All right, let's talk about something that sounds super complicated, but is actually a lifesaver. Newton's divided difference interpolation. I know, it's a mouthful, but stick with me, because at its heart, it's all about one simple thing: making sense of messy, real-world data.
So, picture this. You're trying to track something, right? Maybe it's stock prices, maybe it's the temperature, maybe it's data from some experiment you're running. You've got some data points, but you've also got gaps, big ones. And to make it worse, your measurements are all over the place, not taken every hour on the hour. So what do? How do you fill in those blanks? Well, that's the exact problem we're going to tackle today.
So, yeah, let's dive right into this problem of messy data.
Okay, to really get why this is a big deal, look at this comparison. On one side, you have the dream scenario, right? Evenly spaced data. Everything is neat, orderly, the kind of thing standard formulas just eat up. But then, there's the other side. That's the real world. Your X values are all over the map. A jump of 1, then 2, then 3. It's messy. And your typical run-of-the-mill methods, they just throw their hands up and fail. They just can't handle those random gaps.
And this is so important because, let's be honest, perfect schedules don't really exist in the real world. You've got sensors that glitch out, satellites that only pass by at weird times. Most data you'll ever work with is going to be messy like this. We don't need another tool for a perfect world. We need one that's built for reality.
So how in the world do we connect these dots when the spacing is all wrong?
The secret weapon here is something called divided differences, and the idea is actually pretty genius. Instead of just looking at how much the Y value changed, you also factor in how far apart the X values are. You're basically creating a rate of change, or a per unit difference. It's like you're evening things out, putting all your data points on a level playing field no matter how much of a gap is between them.
You know, it's kind of like calculating average speed. If you just look at the distance, a 10-hour road trip is always going to seem longer than a 1-hour trip. But when you divide by time to get miles per hour, suddenly you can make a fair comparison. Well, that's exactly what divided differences do for our data points. It gives us a fair way to compare the changes.
And this, of course, brings us to the hero of the hour, Newton's amazing solution. And who else but Isaac Newton would take this brilliant idea and wrap it up in this, well, this formula? I know. You see this and your brain might start to shut down a little. It looks intimidating for sure. But here's the key. Don't get bogged down by all the symbols. The real magic isn't in doing one massive, scary calculation. It's actually about building up your answer, piece by piece.
Let's break it down. Think of it like a recipe. First, you start with a base value, your best initial guess. Simple enough. Then, you add a little correction to it, using that first divided difference. That gets you closer. Then, you add another, slightly more sophisticated correction, using the second divided difference. That gets you even closer. You just keep layering on these corrections, and with each new term you add, your estimate gets more and more accurate. It's just a refinement process.
Okay, that's enough theory. Let's see this thing work. We're going to walk through a real example. So, here's our challenge. We've got this data, and we need to figure out the value of our function when x is 8, a point that's sitting right in one of those awkward gaps. And here's our messy data set. Just look at those x values, 4, 5, 7, 10. The gaps are totally inconsistent. This is exactly the kind of situation where Newton's formula really shines.
So to get all the ingredients we need for our formula, the very first thing we have to do is build something called a divided difference table. This is really the heart of the whole calculation.
And voila, here's the finished table. Now you're probably looking at all these numbers and wondering where they came from. It's actually a pretty simple pattern. Each number is calculated using the column just to its left. Let's take that first one, 52. All we did was take the difference in the function, 100 minus 48, and divide it by the difference in x, which is 5 minus 4. That's it. And the best part? For our big formula, we don't even need all these numbers. We just need the ones at the very top of each column, that top diagonal. So 48, 52, 15, and 1. Those are our building blocks.
Now for the easy part. We just plug those building blocks into our recipe. We start with our base value, 48, then we add our first correction term, which uses our target of 8, the first x value, and our first difference, 52. Then we add the second correction, which uses the first two x values and our second difference, 15. And finally, the third correction, using the first three x values and that last difference of 1.
You add all those pieces together, and there it is, 448. It's that straightforward. We just took that messy, gappy data and pulled out a super precise, logical estimate for our missing value.
But wait, it gets even better. This is where the whole thing just gets really elegant.
The true beauty here isn't just that this method works for messy data. It's that it's a universal principle. You know all those other simpler formulas for perfectly spaced data? Turns out they're not different formulas at all. They're just simplified versions, special cases of this one. Newton didn't just find a workaround for a tricky problem. He uncovered the fundamental principle that governs all of it.
And hey, don't just take my word for it. The research makes it clear. The methods for those nice equal intervals, they're just a particular case of this much more powerful formula. So this isn't some niche tool. It's the real deal, the fundamental concept.
So, there you have it. A powerful way to take messy, confusing, real-world data and turn it into something you can actually work with and understand. And that just leaves one question for you to think about. Now that you have this tool, what hidden patterns are just waiting to be discovered in your data?